Okay, so we're going to talk about UART. So this is about communication. And where do you use this communication? Actually, you're going to hook up your MCU to your laptop. You have a console on your laptop, and you're going to use that to communicate with your microcontroller. So the microcontroller needs to be able to know how to send characters over the transmission line to your laptop, which interprets it in its own program, and you will see a letter appearing on the console. Now, you may type something in on your laptop, and that character that you type in will go over, say, the receive line for the MCU controller, who's then interpreting that particular character. So the question is, how do we write that? So how do we write the code for transmitting and receiving characters, and how does it actually work in hardware? So if you're going to look at the data sheet, and over the course of the semester you will be doing that more and more and more, you will actually take the Atmeka data sheet and in chapter 19, and encourage you to do so, you will see this diagram. Now this looks pretty complex. What do we see here? So first of all, we see a baud rate generator, which effectively is just a clocking mechanism to first of all transmit the bits of a frame that represents a byte at a certain frequency, right? But also when you receive something over the receive channel, this is the receive channel, then you need to synchronize your own clock with that of the clock that was transmitting it, so your laptop, right? You were typing in characters. Those characters will go in the laptop's transmit buffer, and that buffer is being emptied according to a certain frequency and transmitted bit by bit over that line that is the receive line for the MCU. So those clocks need to be synchronized. That's very important. So effectively we have a transmission line and a receive line. The transmission line, you can push things into a buffer, transmit buffer, and that will be pushed out over shift register. And for the receive, on the receive end we actually have two registers for receiving information. Now, a clear picture is maybe this one that just bolts down, where we just have the basic components that we need to understand in order to understand what UART is doing. So here we see it. So we have a register for transmission, and we push into that, say, a byte of 8 bits. Those 8 bits are going to be put into this shift register, and then bit by bit it's being transmitted over the transmit line according to the baud clock, right? Now, when this register is empty, then you will set a separate bit in some register, which is called the TX empty flag, and we will come to that later in the slides. And that particular flag, when it's set, the moment that it is set, it can also throw an interrupt. And when you have an interrupt, we will come to that into the next block, you can write an interrupt service routine, and that interrupt service routine would immediately start executing when this interrupt is called. So the hardware creates an exception, it throws the interrupt, everything else is being stopped in your main program, and the ISR, the interrupt service routine that is dealing with this interrupt, is going to be called. Now what is this interrupt going to do then? It's going to say, oh, apparently this register is empty, so I can actually put a new character into that register for transmission. That's what such an interrupt service routine would do. So it's very important to be able to generate those types of hardware events. Now for receiving, it comes into this register, right? It's being pushed in bit by bit, and we, oops, what am I doing? And we see here a two-level buffer, so 2 bytes, and you push in the bits from this register. Once a byte is complete, you say that a character was received, and again, a flag is set, and you can potentially program the control registers in such a way that when this flag is indeed set, so that this happens, then the hardware will throw an interrupt. You can call interrupt service routine that then says, oh, a character just got received, let me immediately fetch it from this buffer. And then I can do something else, and I can wait till the next interrupt is called to get my next character. Now, we're not going to work with interrupt service routines now. We're going to just provide a plain code for putting characters into this buffer, into this transmission buffer in order to be transmitted over the transmit line, and also how to read characters. So let's see how that works. But before we go there, if you look at the data sheet, you will see the abbreviation TX and RX. Now, which pins are actually indicating or used for those two lines? Well, if you look at the data sheet, the general picture of the microcontroller, you will notice that the TX appears here and the RX appears here. So the D1 pin is the one that you should connect to the transmission line, and the D0 should be connected to the receive line. Now, some general information about USART. So first of all, it's a 3-wire cable, a transmission line, a receive line, and also a ground line. It's designed originally for the mechanical printer a very long time ago. You've never seen that. I actually, as a student, when I just started out, we had these mechanical printers. It's an incredibly slow process to print. The protocol is very, very slow. Now you can use this to allow full duplex. That means that you can transmit and receive at exactly the same time. Very interesting, because you can just transmit over the transmit wire, and you can push characters into the buffer, and it is a totally separate piece of hardware from the receive line with its buffer where you receive characters. So you can do both transmission and receiving at the exact same time. Now, to optimally utilize this, we will need interrupts, and we'll come to that later in the next block. Now, what about this clock? So you'll be using a baud rate of 9600 baud, which is in bits per second, which is about 0.1 millisecond per bit. That's really, really slow. So in software, so if you start transmitting a character, right, like that's 8 bits, or in a frame it becomes 10 bits, as you will notice, then it will take you 1 millisecond. That's a huge amount of time. So preferably you want to do something else while you are transmitting a character. So you would only like to fill the buffer and wait a millisecond to fill the buffer again for the next character. In that 1 millisecond you would like to do other kinds of work. And that is what you will achieve by using interrupts, and that's what we're going to discuss later. Now, in theory though, the baud rate can potentially be super large, like 1 megabit per second, but can only be realized if the connection is between MCUs. The used cable is actually limiting the maximum possible baud rate. So, per bit though, we're going to make 4 measurements. So imagine that clearly we're not transmitting bits over a line. It's like a waveform, right? It's like a high voltage or low voltage. So within a certain little bit of time, we see a high voltage, say representing a 1, and then we transition maybe to a little bit of time where it's a low voltage representing a 0, and again a low voltage presenting a 0 again, for example. Now, how do I detect whether I see a high voltage or a low voltage? Well, I want to make sure that I'm not going to introduce errors, so I'm going to sample that little bit of time in which I see the high voltage 4 times. I take 4 measurements, and they all need to match, and then I'm certain that I see, say, a 1 if it's a high voltage, and otherwise a 0. And then with the next bit, when that's being transmitted, say, low voltage or a ground, then I'm again making 4 samples. They all need to match, and if they do, I am sure that I have received a 0. And otherwise, as we will see later on, I will throw an error. So what does that mean though? If I'm going to transmit 10 bits in a frame, then I need 40 measurements, 4 times 10, and they all need to match. That means that the baud rate of the MCU communicating to your laptop and the baud rate of the laptop communicating to your MCU should match within 1/40th or 2.5%. So you need to make sure that they are set at the same amount. So how do you set those? Well, there are two registers, UBRR0H, the H stands for high, and UBRR0L, where the L stands for low. Together you have 16 bits. You'll be using the 8 bits to store the 8 bits, say the lowest significant bits of the representation of your baud rate, and then you need another 4 bits out of those 8 to represent the other bits, and that allows you to represent an integer between 0 to 2 to the power 12 minus 1, which is 4095. So these are the formulas. FOSC is really the clock frequency of your MCU, which we have called also FCPU. Later on I will give some sample code in the slides and you will see that appearing. And the formula is very straightforward. To calculate the baud rate, I have this formula. I take the FCPU's clock frequency, divide by 16, and look at what this register represents, add another 1 to it, and that's the baud rate. But what we will be using is this formula, because you need to set this register. So I'm going to divide this clock frequency by 16 by the baud rate that I want, and subtract 1 from this. Now notice this is an integer division. Okay, so now we have UBRR, and this says just n. Actually it's an integer that lies in this range, and we're going to store it across those 12 bits in the lower and the higher part of the UBRR registers. Okay, so I also want to mention that it's possible to have 2 samples per bit, which is asynchronous double speed. It means that you're transmitting faster, but it means that you have less samples and you're more error prone. So there are disadvantages and advantages, and you can see the 16 here is replaced by an 8, and that makes it all faster. So let's have a look at these 2 registers. So in order to represent my 12 bits, I take the 4 bits over here, 8, 9, 10, and 11, and the 8 bits in the UBRRL register. Okay, so in the data sheet you will often see these kinds of a small n. It simply means that you need to replace by an integer. Depending on your microcontroller, you may have even multiple choices like 0 or 1 or up, and in our case we only have a 0 here. So at default everything is equal to 0, but you clearly need to program it with the 9600 baud rate, and we will come to that later. How do you do that in software? Something about the frame format. Suppose I want to transmit a byte, that's 1 character, so it's 8 bits, so I need to transmit 8 data bits, but I want to start with a starting bit, which is simply a falling edge from high to low. And that is used for the receiving end to start its own clock, so that the clocks are synchronized. So it's just a matter of synchronization. You know that a frame is going to be transmitted. At the end of the frame it's again going to be high, and then you would effectively be able to recognize the start of a frame, and then you will be able to synchronize the clock at the receiving end with that of the transmitter, and then you can start reading, that is sampling 4 times for each of those bits, all the data bits that you want. So we want, say, 8 data bits, so we have 0, 1 up to 7. You don't care about the 8th data bit. You could potentially transmit 9 data bits, but you don't if you only want to transmit a character. So you're not interested in a special parity bit. You need at least 1 stop bit. So suppose you have 1 stop bit, that's say the default frame length. Then we have a start bit, 8 data bits, and 1 stop bit, that's 10 bits. So that's what we will be using. Now, a little bit about hardware. So we have a transmission buffer and a read buffer, right? A receive buffer. And we have only one register name, UDR0, and it manages both. So how does it do that? So actually, when I'm going to read from UDR0, then I'm actually going to physically read from the transmit buffer. If I'm going to write to UDR0, I'm going to write to this particular buffer. If I'm reading, I'm going to read from the receive buffer. And if I'm going to writing, I'm going to write to the transmit buffer. Now, these two buffers are two separate hardware buffers, right? Two separate registers. And that means that I can read and write at the same time. I could potentially read this particular register, but then I'm reading this particular physical register. If I'm writing, then I'm not writing this register, I'm only writing this transmission buffer. So that's important to distinguish. So it's a little bit confusing maybe, but we have just one name to deal with reading and writing from both the receive and the transmission buffers at the same time. Alright, so in order to operate your USART, you have a bunch of control registers that you want to program in the right way. Now, it turns out we have 3 control registers, and we go through the gory details of each, just to show you what kind of things you can do. So this is the first one, A, and we have a B and we have a C. And over here we have this register, but I like to make sure that you're on the same page here. When I talk here about RxZ0, then that means the position to this particular bit in this register. This is a variable. UCSR0A is a variable that you can read and write. You cannot write RxC0. That's not possible. It's a constant. This particular guy is equal to 7. This is equal to 6. This is equal to 5, equal to 4, equal to 3, and so on. The only reason that I introduced these keywords, these constants, right, is to give semantic meaning to 7 in the context of this register. If I want to manipulate the 7th bit of this register in my program, right, I rather want to use this particular constant, because then I can read my own code and say, hey, I'm manipulating or I'm reading that particular bit. Now, not all of these bits are writable, by the way. As you can see, this is only readable. This one is read and write, RW, and this is also RW. The initial value is set to all zeros except for this one bit, which is set to 1. Alright, let's have a look. So RxC0, the 7th bit, is the receive character complete. What does it mean? It means that there is something in the receive register worth reading. So it's an important bit, right? So you notice that if that flag is set, and I poll that, for example, then I know that something is there. So let's read it, so that the buffer is empty and something else can be read again and transmitted to the buffer, yeah?
So RxC0 is just the name for that position in the UCR0A register, right?
Exactly.
So if I wanted to write like a couple lines to say if I've received character complete, it would be if UCR0A, parentheses like for position, RxC0 equals 1, then that means I've received something complete and do some other stuff.
No, that is wrong. So here we have this register. If I want to know what the bit value is at this position, I will simply need to end this register with a register that has the content 000000001. Now how do I create that register? Is by shifting a 1 over 7 positions. I replace the 7 by RxZ0. We will have some examples later on, but then I see that this register is AND, right, with the 8-bit value represented as a 1 left shifted over RxC0 positions. That will indicate that I'm interested in that particular position, and that mask, right, when I figure that, when I do the Boolean computation, will give me either the all 0 value, 0, 0, 0, 0, 0, 0, 0, 0, or, because with the AND operation, it's zeros with a 1 over here. So if it's equal to 0 or not equal to 0, will teach me what the bit value is of this particular flag. So when I'm talking about RxC0, I really mean here the semantic meaning, but in your program, RxC0 has the constant value 7. That's it. So the position indicated by RxC0, 7, that position in this register is having a bit that indicates whether a received character is complete. That's what it's going on. So later on we'll see a piece of code, and you will, and we'll talk about it a bit more. Yeah.
And where's your